If I talk too fast, let me know. I do that sometimes. You just have to kind of stop me and say, I don't understand, or you're going too fast. Okay, so he's starting off talking about sets. Okay, so some of these things you're familiar with. You're familiar with union, right? Mm-hmm. Oh, can you see me? Can you see my screen? Okay, so yeah, so I'm at this part right here. So, whoops, go back for 1 second. Let me erase this. Okay. Okay, so you know about unions. You know about intersections. Are you familiar with this thing called a set difference? Okay, so this is kind of important. So one of the things we do when we think about sets, you have some sort of bigger set, right, that everything sits in, and then you have two subsets, right? Call them A and call them B. Okay? Right. That's right. So the union is basically you put everything together, right? So that would be the union, right? Okay? And the intersection would be what? Right. It's where they overlap, or the elements they have in common, right? Now you notice that there's two areas that we haven't kind of shaded in, right? There's this area right here. Like this part here, okay? And notice what this is. This is all of the elements that are in A, but they're not in B, right? Okay, so the way we write that is we use this thing called a set difference. That's right. And so people write it different ways. Sometimes people write it like this. So sometimes people write it like this. Okay. Sometimes people write it a different way. Okay, they'll write it sometimes like this also. They'll put A minus B. So it's you're subtracting off, right? Okay. Now what's really important is to realize what this represents mathematically. This is actually the intersection of A with B complement, right? It's everything outside of B, right? And so you notice this is what it is. These are all the guys that are in A and not in B, right? So when we talk about a complement, so when we talk about intersection, it's really the same as and. It means the same thing, right? Okay, so that's how we want to think about this, but this is how we write it. And this is called the set difference, okay? And you notice actually down here, he actually writes exactly what I just said. Right, so you're asking what happens if you have B on the left-hand side and A on the right-hand side? Okay, then we follow the same sort of formula. We say B slash A is basically all the guys in B. Exactly. So we write this as B intersection A complement. That's right. A very important thing to understand about sets, and this is something that we're going to do over and over again, is we're going to note the following thing. When we have two sets, A and B, okay, I can rewrite A in terms of two parts that are disjoint. So So before I explain this, let me define what disjoint is. Do you know what disjoint means? Good. So disjoint means that the intersection of those two sets is the null set. They have nothing in common. So it means that A intersection B is equal to, exactly, okay, good, he uses that notation, that's right. It looks like a phi, that's right. Okay. So this means that these two sets don't overlap. They have nothing in common, right? Okay, now what I want to show is the following. I want to show that for any two sets, whoops. Let me think about that if I want to do this as a proof for a minute. Let me state it as a fact. Let's state it as a fact, and maybe we'll want to come back and prove it a little bit later. So we'll just say this is a theorem for right now. Okay, so we'll say theorem. So we're going to say that we can rewrite A as A is equal to the union of two sets. The first is going to be A intersection B union A intersection B complement. Okay. So let's look and see why this is true. We can prove this, but let's look and see what it's saying. So I'm going to go back for a second. Since you had this on video, I'm going to erase all this, okay? Because you'll be able to see what it looks like. And I'll write this over again. And you know, we will actually prove this. This is something that you should be able to prove, and Ela would probably ask, okay? Okay, so here's my two sets, A and my other set B. I'm going to put it in a different color. No, they aren't disjoint. They're going to overlap. Okay, but what I want to show you now is I want to show you that that's what I want to do. Color this red. Okay. So let's go ahead and call the black one A. Okay. Here we go. And what I want to impress upon you is the following. So, whoops. Let me undo that real quick. I have to erase it. Okay. So I'm going to do this. I'm going to draw in A intersection B. That's this, right? Yes. And now I'm going to draw in A intersection B complement. And that's this. Okay? So the green is all the people in A, but not in B, right? Okay, good. So now you notice something. These two things, they're disjoint, right? Because this guy here is A intersection B complement. The other one's A intersection B. They can't have anything in common, right? So these two things are disjoint, right? Okay, but their union is what? Exactly. So we're going to use this over and over again. We're going to decompose sets like this, okay? Okay, good. One thing that's very important that he didn't talk about that you really have to understand is that is the issue of how you prove two sets are equal. Okay? So another thing that we have to know about sets is we have to be able to prove that A is equal to B. So how do we do that? How do we prove that two sets are equal? prove that. Okay, so so you're right. One way we could show that, one way we could maybe show that is show that the intersection is equal to both of the sets, right? But there's actually a more standard way. So one way we do this is, and this is something that you wouldn't know, okay? This isn't something that you're expected to know, okay? So how to prove A equals B. My laptop broke down, so I have to do this by hand. So it's they're going to fix it this week. So this is a little scrawly, but that's okay. So think about what it means to have a set. A set. What we're interested in a set is we're interested in who belongs in the set, right? So the first thing we have to show is we have to show that everything that's in A is in B. Right, so the first thing we have to show, the first thing we prove is we prove that A is a subset of B. Okay, and then what do you think the second thing we show is? Exactly, that's it exactly. So these guys must have the same elements because everything in A is in B and everything in B is in A, so they have to be the same set, right? Okay, so we're going to use this, okay? This is how we prove two sets are equal, all right? It isn't like proving two numbers are equal. It's a very different thing, right? Okay. Now, so these are kind of two important things to start off with, okay? Let me just kind of back up here for a second. So, definition of disjoint is very important. The fact that we can decompose a set as a union of two disjoint sets using another set. How we prove two sets are equal. And the last one is hard. So the last one is called De Morgan's theorem. Okay, so this is one version of De Morgan's theorem. Okay. And it's actually quite hard to, usually we can draw these nice pictures. Like we talked about union, intersection, how to decompose sets. I could draw these nice pictures, right? This one you can draw a picture for, and he actually tries here to draw a picture. I'm going to show you what he did, but you have to be able to prove this, okay? So here he's looking at the complement of A union B. Okay? So this is the union of A and B right here, right? Right. So he draws these arrows to show that it's everything outside of that, right? Okay. And what he's trying to show is that it is equal to, we should actually put an equal sign here, A complement intersection B. So this is A complement intersection B complement. Okay. That's right. And so you notice that when you take the intersection of the complements, okay, so let's just take a look at this for a second. So I want to look at the intersection of the complements. So this is everything outside of A. Okay. And this is everything outside of B. Okay. And you notice that when I take their intersections, okay, notice that the intersection here, when I take the intersection of this with this, okay, let me just try to be a little more careful here. Okay. So here's everything that's included here, everything except what's in B, right? Notice that when I take the intersection of these two, and this you have to look at it a little bit, this guy does not get included. Okay? So this is not in the set, and when I take the intersection, this isn't in the set, because this is in this set, but it's not in this set, right? Okay, so to begin the intersection, it has to be in both sets, right?
Yes.
Okay, so you notice that this portion is in this set, but it's not in this set, right? So when you take the intersection of these two, you end up getting everything outside of the union. Okay, here's here's what I'm going to do. Here's what I'm going to do. Let me do it this way. I don't like his drawing. Let me do a different drawing, okay? Okay. So, here's what I'm going to do. I'm going to draw A and B. And then we'll draw B. Okay, let me make that a different color. Okay. And the first thing I'm going to do is I'm going to draw B complement in yellow. Okay? Okay, so a B complement. Let me see where my thing is. Yeah, here I am. So B complement is a lot of stuff to color, right? That's right. But I'm going to try to do this carefully so you can see what's going on. Okay. Okay. Yeah, it's it. I should use a. Hold on one second. Sorry. Let me use a. I have a thicker brush that will make this faster. Actually. Oh, come on. There we go. I want the really thick one. There we go. Okay, this will be faster now. Okay. So this is B complement, right? Okay. Daggone it. Oh, man. Drawing is my worst subject, I swear. Okay, let me just... Okay. I'm going to make little pieces so if I screw up, I don't erase everything. There, that's okay. Now I can just go back and I don't erase everything. Okay, hold on a second. Here we go. Okay. In the end, we're going to prove this anyhow. So we don't like using diagrams and we don't like using pictures in math if we can avoid it. But it's kind of helpful here. Okay. Okay. So this is B complement pretty much, right? Okay, I'm going to draw A complement in another light color. I'm going to draw it in, let's see, let's draw it in orange, light orange. Okay, so A complements everything outside of, whoops, I need to draw it in a different, deeper color. Let me draw it in green. First, you know, it's not, it's weird, it's not, oh, hold on, I gotta change the color. It didn't change the color for some reason. Oh, I know why. There we go. There we go. Okay, so now, what's going on? Okay, I think, what the heck? What is going on? It's not changing the... Okay, there, let me just do it this way. Okay, this will work. Here we go. Okay, so this is A complement, everything outside of A, right? Okay. Notice what they have in common. Where do they overlap? Oh, actually it goes like this, right? Yeah, this is A complement. Okay. But notice where they overlap. They only overlap outside of both circles, right? And that's the union of, that's the complement of A union B, okay? That's the idea. Okay, but we have to prove it, okay? And so we have to actually look at the proof, okay? So here he's trying to, so let me think about whether or not we want to prove this or not. So this is how he starts to prove this. He's showing that if X is in here, it's in here. Okay? This is going to prove that this is a subset of this, right? Okay. Okay, right. So he says, okay, if X is an element of this, then X is not an element of A or an element of B. Okay? And let me show you this. This is actually kind of a better way of doing this. So, when we want to prove that X is an element of the complement of A union B, we're gonna say this in a different way. Okay? Instead of saying that X is an element of this, we're going to say X is not an element of A union B. It's the same thing, right? Okay, X is not an element of A union B. And now I'm going to use logic. I'm going to rewrite this as a logical statement. Okay? I'm going to rewrite not here. Okay? This little squiggle means not. Okay? So it is not the case that X is an element of A union B. Okay? So this is saying that it is not true that X is an element of A union B. Okay? Now this is very important. A union is the same as or. Okay? So I'm going to rewrite this inner part like this. Yeah, be careful, because here's an element, so it is, right? So if X is an element of A, X is an element of A, or X is an element of B. Okay? But I still have my, yep, you're right, I have my not outside, right? That's right. So notice I've just worked on the inside, right? Now, we're going to use a very important thing in logic. When we have two statements, so this is where you're learning about proofs here, okay? When I have the statement not P or Q, these are statements, okay? The negation of this is equal to not P and not Q. Whoops. Okay. So this is a fact from logic that we can use. So whenever we distribute a negation or a not across an or, we negate both of the statements and we change the or to an and. Okay? So let's do that here. So what is the opposite? So what I want to do is I want to change this to the opposite. So what's the opposite of X is an element of A? Okay, good. Oh, okay, you actually went ahead of me. Okay, good. Right, X is not an element of A, or X is an element of A complement, right? Very good. And I said that when I brought that not across, I had to change the or to an and, right? And of course, you know what goes on this side, right? X is an element of B complement. No, because notice when I distribute the not through, this is what happens after I distribute the not. When the not comes through, it changes both of these guys, it changed, hold on a second, find out where I am. Here I am. It changed the P to a not P. See? It changed the Q to a not Q. And it changed the and to an or. Mm-hmm. Exactly. That's right. Now notice something very important. A union is an or. What do you think an and is? If X is an element of A and X is an element of B, how can I rewrite that? Bing. Intersection. Bingo. So this is a very important idea. The fact that union is the same as or. And just like you said, and is the same as intersection. Okay. So it's an element of A complement intersection B complement. Okay. And so notice, now, so why did I go through all this work, right? Okay, well, what did I show? I showed that if X is in this set, let's look at the big picture, okay? I showed that if X was in here, this meant that X was in here. Okay. Well, that's how we proved that one set's a subset of another, right? I proved that any element from this set is in this set, right? So what I actually proved is I proved that A union B complement of the whole thing is a subset of the intersection. That looks like a, hold on, that looks like an element. I don't want to do that. There we go. Okay. Now, there's something important to understand. Each of these steps is reversible. Good question. That means that each of those steps can go backwards. For example, if X is an element of A complement intersection B complement, then X is an element of A complement and X is an element of B complement, right? So that goes backwards. This goes backwards also. If not P and not Q is true, then I can take the negation of the or, right? So that's reversible, right? And this is obviously reversible because it's just the definition of union. And this is reversible because this is just rewriting the original statement. So notice I proved the other way too. Okay? That's right. That's right. Because notice what equal means. Equal means that you have to prove that A is a subset of B, but then you have to go backwards and show that B is a subset of A. Right, and how we actually do this in mathematics so that we save time is we write the word if and only if. Okay? So I write here, I write if and only if. And what that means is that this statement goes both ways. If X is an element of the complement of A union B, then X is not an element of A union B. And if X is not an element of A union B, then X is an element of the complement of A union B. It goes both ways, okay? And I keep on writing these if and only ifs. Sometimes people write a double arrow. You can write a double arrow too. It means the same thing. I like the double arrow because the double arrow shows you that it's reversible, right? So a person can look at my proof and they can automatically see that I'm proving both ways at the same time. Exactly. Now, be careful though. You have to be careful that the steps are really reversible, okay? Notice that here all I'm using are really definitions and logic. So as long as I'm using definitions and rules of logic, they will always be reversible. But be careful. You can't just automatically say that a statement that goes one way goes the other way, okay? Okay, good. So the other thing that you have to prove, there's actually another version of this. So there's two statements in De Morgan's law. So De Morgan's law actually has two parts. I'm sorry? Right, so we're actually De Morgan's law. Okay, we're right here. And notice we didn't have to do, he actually does two different proofs, okay? But you can convince yourself that what he's doing, he's actually done in words the same thing we did in terms of symbols. Good. And by the way, you can use either way. For example, his proof is just as valid as this. It just depends upon whether or not you can understand why what he's saying is true. Like, if you can understand why these steps are the way they are, then go ahead and use his method. Okay? But this is a more formal mathematical way of doing it. Explaining everything, okay? Okay. So here he wants you to prove or disprove this statement here, okay? And so notice that, for example, they have an equal sign, okay? And you might think that we have to prove this both ways, and we could. But sometimes we don't have to. Sometimes we can use set identities. Sometimes we can use rules about set operations to prove something is or isn't true, okay? Let me give you an example of what I mean, okay? This is false, and I'm going to show you why, okay? So let's start off with A union B. Let me do the following. I'm going to put a little bit of space between here. Hold on a second, so that we have a little bit of room here. And that's okay. You know what we wrote, so I won't worry about this part. Well, it wasn't the most important part. Okay. What I'm going to try to point out to you are the really important things that you should know extremely well, okay? Here's an example. So we want to prove or disprove this. A union B set difference C is equal to A union B set difference C. Okay. So we want to prove or disprove. And I'm going to disprove it. Now here's the thing. Very often when we start proofs, we actually like to know if it's true or not. And then that determines how we're going to prove it, okay? But in this case, we really can't know. When it says prove or disprove, we really don't have any idea. So here's what I'm going to do. I'm going to start off with this side, okay? And I'm going to use some set operations. So the first thing I'm going to do is I'm going to rewrite this. I'm going to say this. I'm going to say that A union B is equal to A union B intersection C complement, right? Okay, so this little c now means complement. C is a set and C is a symbol for complement, right? Okay. The one thing you should try to do whenever you write a proof is every line you write, you should try to explain why is that true. Okay? So this statement is true because this is the definition of set complement, right? So this is really a definition of set complement. This is how we defined A/B, right?
Yes.
Okay, so this is a definition of set complement. Exactly. Okay. So the first one we know for a fact is okay. And it goes both ways, right? Okay. Now, here's a very important rule that we have to know. I'm going to introduce. If we have an intersection outside a union, we can distribute that intersection. Okay? So one way you can think of this as, like multiplication. Okay? So we know that, for example, if we had numbers, right? If we had A plus B, and we had a C outside, we could distribute the C, right? Bingo. We're going to do the same thing here, except we have to be a little careful. What we're going to distribute is we're going to distribute the intersection C complement. This whole thing. And so this is a fact. This is an important fact, so I'm going to write it in red. So this is equal to A intersection C complement union. The union is between them, right? Bingo. Okay. Now, this looks a lot like what we're trying to prove, right? What looks like the thing that we're trying to prove? Well, we're trying to get to this, right?
Yes.
And isn't this the same thing as this?
Yes.
Sure. So notice what we've proven. We've proven that this is equal to A intersection C complement union we'll just call it slash. That's good enough, Okay. Now, are these two things equal? No. Right? I mean, clearly, these two sets are not necessarily the same. Okay? But notice we can't. Okay, we can't. This is equal to this, so we can't get around this. Okay. Okay. They're not equal. Now here's what we have to do, though. We have to prove it. Okay. Here's how we prove it. I can get a counterexample. Do you know what a counterexample is? Okay. So here's what a counterexample is. Suppose you say something is always true, okay? So you say to me, Matthew, you're always late, okay? Every time. In order to prove you're wrong, what do I have to show? One time, right? If I was on time one time, you're wrong, right? So if I can come up with one example where these two things are not equal, that's my counterexample, right? So let's make a set. Let's make some sets here, okay? So he actually gives us, and so he's actually showing with a counterexample. Let's go ahead. We'll use his example since right. This is one of the ways you can prove this is false, because now I know from this identity that they're not true, so I can easily find a counterexample. All I need to do is I need to make sets A, B, and C in such a way that A is not equal to A intersection. Okay. So what I need to do is I need to find three sets A, B, and C. So A intersection C complement is not equal to A. Okay. Now here's what I'm going to do to make my life really easy. I'm going to make B and C be disjoint. Okay? Because if I choose B and C to be disjoint, this is just equal to B. Okay? So let me go ahead. I'm going to make... go ahead, go ahead.
B is 2 and C, so there's no common symbol between B and C.
Exactly. Exactly. And so I'm going to make C be equal to 2, 3. Okay? And now I'm going to make A have a little bit of overlap, okay? I'm going to let A be equal to 3, 4. Yep. Exactly. So, and really all I have to do is I have to make sure, the only thing I have to make sure is I have to make sure that these two are not equal. That's all I need to do. In other words, I need to have one person in C complement that's not in A. Okay, that's a good question. So let's let everything be equal to 0 through 4. So we call this the universe. This is all the numbers, okay? Yep, I'll let that be everything, okay? Okay. Good question. Okay, so now let's show this is wrong. So let's look at what is A intersection C complement. Well, C complement is what? Bingo. Okay, what is the intersection of A with C complement? Bingo. Okay. What is B intersection, I'm sorry, B slash C? B intersection C complement. B intersection C complement. C, because C complement, because I want B slash C. That's the intersection of B with C complement, right? Zero, 1, okay. So now let's form these two sets, okay? So A union B slash C is what? Let's write down A2. A is equal to 3, 4, okay. So now if we look at this, A union B difference C is what? That's right. Exactly. Uh-huh. Right, so what this means, B slash C means B intersection C complement. It's all the things that are in B and not in C. That's right. That's right. Sure. Uh-huh. So X is in B and X is not in C. Okay. And so you can see, if you the one thing you want to do is you want to be able to take words and translate them into mathematics. So this is a good example because notice what I can do now is I can write this as this is the same as saying X is an element of B, right? And X is not an element of C, or X is an element of C complement, right? And I have that and between them. And that's what allows me to say that. Okay? So just how you translate Arabic into English, we have to translate English into mathematics. So you have 3 problems. Translate Arabic into English and then English into math. Okay? Okay. Okay, we're almost done. So we have the first one. This is the first one we want, right down here. Okay. And now let's look at the other one. The other one was A intersection C union this, right? So this was the other part. We're trying to prove A, I'm sorry, A what the heck? Where did I write? I didn't write it. Sorry. This should actually be this should be A intersection C here. Sorry. Let me rewrite that over. It's a little confusing. Let me make sure I have the statement correct. Hold on. No, I'm sorry. It was A union B intersection C. Sorry. Yeah, I had it right the first time. Okay. Right. What I wanted to show, I know what I wanted to show now. So here's the point. This is what we get to. So this was the set that we've just done is this set here. Hold on a second. Yeah. Right. So what we've done so far is we have done the right-hand side. Okay. Now what we showed was, this is the important part, we showed the left-hand side's equal to this. This is the left-hand side. So that's what we need to do now, okay? So notice we have A intersection C complement, and we have B subtracted from C, right? So I can take their union, right? And so let's, bingo, exactly. So now we can see those two things are definitely not the same, right? Exactly. So now we've proven by a counterexample that they're not the same. So the way we'd say this in mathematics is we would say, these two, we have found a situation, a case where these are not equal, therefore this is a counterexample proving this is not true. Okay? So these are some important laws. These are a lot of good set theory here. Okay, so any questions on what we did? I know it gets a little confusing. There's a lot of sets we're working with. Good. Yeah, I think the video helps a lot to be able to go back. It's very hard to take notes in a class and listen and watch and understand. It's too hard. Even okay, so this is kind of the same sort of thing. When we're trying to prove or disprove, we're going to do the same sort of thing. We're going to use different sorts of set operations and do the same sort of thing. We're going to show that one side is not the same as the other, or that they are the same. Okay? So some of these will be true, some of these will be false. I'm trying to think if we want to do these now or we want to move on to something else and you can try these. Sure. No, I understand totally. So, right. Okay. Okay. Let me take a real quick look at the homework. It's I haven't actually. I have the book. I actually have Abbott. So let me look real quick and see how hard they are. When is the homework due? I'm sorry?
Let's recheck.
Sure. 1.25. Okay. 1.210. Okay. Okay, so that's this Thursday. Yeah. Okay. So, so we have some work to do. Let me think for 1 second. Let's see. Let me see how much more he wrote in the introduction here. Let me just see. Okay, it doesn't have that much more. Definition of a function. This is an important definition. The image and the pre-image. Let me go through this, and then we can start on section 1.2 because you're going to need that to do the homework. Sure. No, I understand. Right. And here's the thing. You don't have to know all of the material right now. I mean, we can come back and pick up some of those things, okay? So let's look at 1.2 because 1.2 is going to be an important section for you. Okay, so he's starting off, he's saying, so he's talking about sets, okay? The empty set, okay? Here he's talking about what it means to be a subset. So here he's talking about definition of subset. This is important. But you know what that means. Yeah, so and let me actually write it out. So this is kind of a good thing to write out, just to be careful. So when we say that A is a subset of B, what this means is that if X is an element of A, what do we know?
It's also in B.
That's right, implies X is an element of B. Okay. So, exactly. So the picture we want to draw is something like this. This is B. This is, A. Okay? And so everything in A is in B. Okay? It's very important. One of the things that's important to know that sometimes they don't tell you is that the null set is a subset of every set. Okay? So it's important to know that for every subset C, or for every set C, and we don't have to explain why, but this is a fact. For every set C, the null set is a subset of C. That's right. Null set. And I won't explain why. Right now, we're gonna believe that that's true. Okay. Okay. Good. Okay. So this is what it means to be a subset. The null set's a subset of every set. Exactly right. So this is this portion right here, huh? And I'll tell you what. I'll just highlight the important parts, so that way you'll know what to read and what not to worry about as much. Okay. So the definition of null set is important. The definition of disjoint's important. Both. Exactly, both. You have to read it, but then you have to be able to understand it. Which really means you should be able to explain it. One thing about ELO is he might ask you questions too. He might ask you like one-on-one stuff. Okay, so this is all important right here. Okay. But that isn't a lot of reading, right? That's pretty small.
So, the set 5 is called the empty set.
Yes. Right?
To be the set that contains all elements. So that is
Okay. Okay, so now he's referring to, so you have to go back a little bit. He's actually talking about this statement right here. This statement here is what he's referring to. And equivalent means that it's the same as. So he's saying that saying the intersection of E and S is equal to the null set is the same as saying they're disjoint. Okay, so in a sense he's actually defining disjoint. He's saying disjoint is the same as the intersection of two sets that's equal to the null set.
so
Yes, absolutely.
since we have just used the notation, I didn't get this.
Right. So what he's saying is you're saying that these two sets are equal. Right? But you haven't even defined what it is. So now he's going back and saying, "Hey, hold on a second. We're talking about something up here that we haven't even defined. So let's go back and define it carefully." Okay? It's kind of a long-winded way of saying that. Okay.
Okay, so
Right. And this is the key step. This is the thing that you want to pay attention to. To assert. That's the most important thing, okay? That's right. Exactly. Okay, good. I like the way you're doing it. You want to start off and understand the basics well. Oh. No, you'll do well. Don't worry. I promise you. Trust me. Okay, here he's giving an example, and this is a little important because you're going to come across these pretty soon. Notice that, and I'm going to kind of draw these. Okay, let's just draw a number line here. So 1, 2, 3, 4, 5, ... Right? Okay, notice that A1 is the set that starts at 1 and contains all the integers, right? So this is A1. Okay? Now notice A2 is contained inside of A1, right? It's all this. Okay. So A2 is a subset of A1, right? Now notice that A3 is actually contained in both of them, right? This is A3 right here. Right, and you should convince yourself. Don't just say yes, okay? So is everything in A3 and A2? A2's the green, the bluish type. Is everything in A3 and A2? Sure. And everything in A3 is in A1 because it's even bigger, right? Okay, good. So notice what we have here is we have kind of like a bunch of subset relationships. Every set after this is contained in the one before, right? So sometimes we call this sort of thing nested. In other words, nested means that it's inside, right? So it's kind of like a bunch of boxes. You have a big box and then a smaller box inside and then one inside of that, right? That's what nested means, okay? That's the idea. Okay. This is an important notation. This notation here. Notice now that I don't have a finite number of sets, okay? This is actually A1, A2, A3, ... right? Exactly. And sometimes we call this a family of sets. A family of sets. Notice what this means. This means that you're in A1 or in A2 or in A3 or in A4, okay? So in order to be in the union, you only have to be in one of them, right?
Yes.
Okay, good. So if I'm in A1 and I'm not in any of the others, for example, notice that 1 is an element of this union, right? Because 1 is in A1, and it doesn't have to be in the other ones as long as it's in 1, right?
Yes.
Okay, now look at this. This is the intersection of all... I'm sorry. This is the intersection. And actually what he's trying to show you, this is a good thing to convince yourself. This is something that you should see if you can show, or at least make sure you understand. So this is something that you should check. Make sure that you believe this.
The same thing you told me just say.
Right, and the reason why this is true is because if you're in A1, you're automatically in all the others. Okay, so you notice that A1 is a subset of this union. Okay, A1's contained in the union, and everything in here is in A1, because if you're in A1, you're in A1, but if you're in A2, you're in A1, okay? So it's a little tricky, but okay, that's good. Here's the hard part, the intersection. So that when you're in the intersection, it means that you have to be in all of them, right? A1 and A2 and A3 and A4. Notice something. There is no number that is in all of the sets. You're not sure, okay? Okay, let me go ahead and prove it to you. You give me a natural number, any natural number at all. Say for example, you tell me I don't believe you, and give me a natural number that you think is in the intersection.
Like to say
4. Okay, good. So you're claiming that 4 is in all of them, right? Okay, let's look at A5. What is the set A5? If 4 is in all of them, it has to be in A5, right? So notice, exactly, because A5 starts at 5, exactly, right? And see the point. No matter how big a number you take, I take one bigger, and it's not in that set. Okay? All right, good. And so down here, he makes this argument. He actually says what we just said a second ago. So he's actually taking this argument and he's saying the same thing right here. Okay, good. Okay. The complement we talked about, let me highlight this. It's all of the elements that are not in A. Very important definition. Now, remember I told you that there are 2 forms of De Morgan's law, right? Okay, these are the 2 forms. Okay. We did this one right here. Oh, what the heck? Hold on. We did the one on the left, right? Yeah. We did this guy right here. Okay. Never mind. For some reason I can't do this. All right. This is the guy we did. Now, I won't bother. We should come back at some point and do the other one. But for right now, let's just believe these. But here's the important thing. Here's what you want to notice. You want to look at the pattern. Look at what's happening here on this side. you're taking the complement of an intersection. Okay? Now what happens? What happens? These both of the sets turn to complements. Exactly. Notice the same thing happens here. When you take the complement of a union, both of the sets become complements and the union changes to a complement. Okay? And the reason why, there's actually a reason why. We actually discussed this. We showed that if you take not P and Q, it's equal to not P or not Q. That was the left-hand side, okay? And you can show the same thing with an or statement. The not of an or statement is an and statement. Okay? But we don't have to worry about that too much. Right now, you just want to memorize these. So let me put a little thing. We'll say memorize. And what you really want to notice is the pattern. When you have a complement, it changes whatever that thing is to the opposite. It changes to union to an intersection, intersection to a union, and it takes the complement of all the sets. Okay, good. Functions, I tell you what, I'm not going to worry too much right now about functions. He didn't ask you any homework about functions. We will come back to functions. This section is very important. But for right now, I'm just going to skip this, okay? Okay.
So in my class, I said, where did it stop?
Actually, in the paper, he stopped relatively early. He stopped. Hold on, sorry. He stopped. He stopped at functions. Oh no, he didn't. Hold on. Yeah, he went to functions. Yeah, so basically he stopped at functions. You are going to have to know these things, but he didn't ask any homework on it. Okay. Right, we can do the homework first, and then if we have time, we'll come back and we'll deal with these. Okay? Okay. Okay, great. So let's look at the homework. So the one thing he's talking about is the triangle inequality. So he gave a homework problem on this. This is a really important thing. So let me do the homework problem on triangle inequality, and then I'm going to talk about it a little bit. Let's see, 1.25. Here it is. I'm going to take a screenshot real quick. And, yeah. Paint. Okay. All right. So this will be homework problem 1. Okay, yeah, right. Homework 1.5 point. Okay, good. Okay, and we may want to do both. Let's just see real quick. Okay. So there's a couple of things we need to know about the triangle inequality. This is a really important result, okay? So if you notice that that's okay. This is something that it's not hard, but it takes a little bit of time to get to understand. Okay. So here first we're gonna define what the absolute value of x is. We're gonna give a definition. Okay. So this is equal to x if x is greater than or equal to 0, right? And it's equal to minus x if x is less than 0, right?
Yes. It could be
Right, because if x is less than 0, then x is negative, right?
Yes. Things like this section. Things we actually beside the x. Keep the minus 1 plus, right?
I'm not sure I follow.
Do you see that the x are just 1?
Me here?
Yeah, the left.
The absolute value?
Yeah, absolute value.
Uh-huh.
Make it the negative and positive, right?
Exactly. That's right. So as an example,
Able to be negative minus x.
yeah, and here's the reason why. Let's just take an example. So what is the absolute value of negative 1? What is x here? X is negative 1, right? What is the absolute value of negative 1? Right. And isn't 1 negative of negative 1?
Yes.
Which is negative x, right?
Yes.
Okay, good. So all we're saying is that we're just changing the sign on a negative number and making it positive, right?
Yes.
Now, notice something important. What does the absolute value represent? What is the interpretation? So what is the absolute value of x? What does it mean? Well, let me go ahead.
How far is from this the 0?
Exactly.
The number line?
Bingo. It is the distance of that from 0. Exactly. It's the distance of the point. It's the distance from the point to 0, which is why it always has to be positive, right?
Yes.
Good. Okay. Okay. Now we want to prove some facts. We want to prove some really simple facts from x to 0. Okay. To the origin. Okay. We want to prove something that seems really easy, but we have to prove it. So this is the first thing we're going to prove. We're going to prove that the absolute value of x is always between I'm sorry, let me do it this way. Let me think for 1 second real quick. Actually, I want to back up. Let me do it this way. I want.
So now we are not solving A or B.
That's right. We're just dealing with one thing right now.
We are just like to understand it.
Exactly. So this is the first thing we want to prove. We have to prove that x is always between the negative of the absolute value and the positive of the absolute value. Okay? Now there's different ways we can prove that. One of the ways we can prove that is we can look at the different cases for x. We can look at the case when x is positive and x is negative, right? So we have two cases. We can look at the case. We can prove this is true when x is greater than or equal to 0. That's our first case, right? Okay, so let's go ahead and do that. So when x is greater than or equal to 0, we know that the absolute value of x is equal to x, right? Which is greater than or equal to 0. So this is from the definition of absolute value of x when x is greater than or equal to 0, right? If I multiply both sides by negative 1, what happens? Well, minus x becomes, minus absolute value of x becomes less than or equal to 0. Okay, because when I multiply by negative, I reverse the inequality, right? So now look what I have. I can put this all together. I can say negative absolute value of x is less than or equal to 0, which is less than or equal to x, which is less than or equal to absolute value of x. Okay? And I'm going to let you do the other case. So I'm going to leave it for you to show. So you can do this as an exercise. You can do the other case now. And I claim you'll find the same thing, okay?
So, x less than 0.
Mm-hmm. You want to try it?
Yeah.
Okay.
X less than 0, so we multiply it by x, right?
Okay, right. So we know the absolute value of x, right, is equal to what?
X less than 0.
Is equal to negative x, right?
Yes.
Okay. And we also know that x is less than 0, right? Okay.
So we can say yes.
Okay. So let's think about this for a second. So I want to kind of hook these two things up, right?
Yes.
So what if I multiply by negative 1 here? What would I get? I'll get negative x is greater than 0. Okay. So now I have the following. I have that the absolute value of x. Hold on a second here. Absolute value of x, which is equal to minus x, which is greater than 0, which is greater than x. Okay? And so now we still have one more thing we have to show. We have to show that this is greater than or equal to minus the absolute value of x. But notice that I can get this because this is a little bit of work. Notice that if I multiply this side by minus 1, I get that x is equal to minus the absolute value of x. So since it's equal, it's greater than or equal to, let me make this a big view, minus the absolute value of x. Okay. I'm trying to prove this right here. Okay. And so now I have what I want. I have, if I look at this final result, I have that, where's my pen? There it is. I have that minus absolute value of x is less than or equal to x, which is less than or equal to the absolute value of x. Okay? These proofs, they take a little while, but they're really good proofs to practice. Okay. Okay. So now we want to prove something that's important. This is called the triangle inequality. So this is the first result. We'll call this theorem 1. It's probably in the book. Let's look and see where it is in the book. In the book, let me see real quick. It's on page... he doesn't actually give it. He doesn't give this result. Okay, but we're going to need it. That's okay. Okay, so the last thing we want to prove before we can prove this is we want to prove what's called the triangle inequality. This is one of the most important results in analysis. It's called the triangle inequality. And this is in the book. In fact, this is on page... this is this theorem right here. Okay?
Okay, so it has like cases.
No, actually we can use that result that we just had a second ago. Okay? So we're going to prove it right from that. So I'm going to prove the triangle inequality.
We're gonna use that for solving.
Exactly. We're going to use that a lot. We're going to use these two a lot. So we want to prove the triangle inequality. And here's what the triangle inequality says. It says that if we have any two real numbers, a and b, it says the absolute value of a plus b has to be less than or equal to the absolute value of a. Right. Okay. And what it's saying is, if you kind of think about it, we're going to use this in a lot of different forms. But one way of thinking about this is, if you think about kind of a triangle, right? And this is A and this is B. It's saying that the length of this side is always less than the sum of these two lengths. Okay? So it's and you can see it's true for triangle inequality, because if I laid B down here flat, if I flatten this out, this was B, right? This would be A plus B. It would be its longest when I took this triangle and smashed this onto this axis, right? But if I bring it up, if I bring the triangle up, this becomes smaller then, right? But A and B don't change. Good, good. Okay, we want to prove this. So here's the proof. So we start off, and here's what we know from last time. We know that minus the absolute value of A is less than or equal to A is less than or equal to the absolute value of A. We just proved that, right? Okay. We know that the negative of the absolute value of B is less than or equal to B is less than or equal to the absolute value of B, right? Now, I can add these two inequalities because the signs are going, the directions are going the same way, right? Okay, so this is going to be minus the absolute value of A minus the absolute value of B is less than or equal to plus B. Right. Okay. Now notice something, that suppose, for example, A plus B was negative. Let's just look at two possibilities here real quick, right? So if A plus B was negative, okay, when I took the absolute value, this would be larger than this, right? Let's think about this for a second. If A plus B is less than zero, right, it's negative. But this is more negative, right?
Yes.
Okay, so when I... Go ahead. Exactly. So when I take the absolute value of... And I'm going to rewrite this. I'm going to be kind of sneaky. I'm going to rewrite this like this. Absolute value of A plus the absolute value of B. I'm just gonna factor out a -1, okay? Okay, good. Okay. So now I'm gonna say that I know for a fact now that the absolute value of -1 times the quantity absolute value of A plus the absolute value of B is greater than... Gotta be careful and close these things off well, is greater than the absolute value of A plus B, right? Now I'm going to use a theorem. We didn't prove this, but it's not too difficult to prove. We're going to use a theorem from the book that says this. It says the absolute value of a product is equal to the product of the absolute values. Now, this isn't hard to prove, okay? Because think about it. If you have a positive times a negative, the absolute value is just a positive times a positive, right? So this is, I'm not going to prove it, but you can do all the different cases. You can do 4 different cases, and you can prove to yourself this is true, okay? But it's kind of obvious because the absolute value of a product is just equal to the 2 positive values, right? Okay, good. Now, notice what I'm going to do. I have the absolute value of negative 1 times this. So this can be written as the absolute value of negative 1 times, sorry, maybe that back up, we'll do this one more time. The absolute value of negative 1 times the quantity absolute value of A plus the absolute value of B. Okay? Now notice, what is the absolute value of negative 1? That's easy, right? Just positive 1, yeah. Exactly. So now I get what I want. This is what I want to prove. And notice the other way is actually exactly the same. If I go ahead and I assume that A plus B is greater than 0, then the absolute value of A plus B is equal to A plus B. If this is positive, it's equal to its own absolute value, right? So if I suppose that A plus B is greater than 0, then I know that the absolute value of A plus B is equal to A plus B. Okay, because the absolute value of a positive number is equal to itself, right? Okay, let me back up. Let me write it again. It's a little bit messy. Okay, so if I told you that the absolute value of A plus B is greater than 0, so if I know that A plus B is greater than 0, then it's equal to its own absolute value, right? If this is true, then what is the absolute value of A plus B? Let me ask you a question. What's the absolute value of positive 2? Exactly. So the absolute value of A plus B is just... Exactly. Good. And I know from this line right here that this is less than or equal to the absolute value of A plus the absolute value of B. And that's the proof right there. That's the end of the proof. So we proved it's true for both cases, and this proves the triangle inequality. Very, very important inequality. It's a good idea to practice proving these, because these are things that we use a lot. We have to feel very comfortable, okay? Okay, so let's prove your problem, okay? This is tricky. It involves a little trick. Let me show you the trick. Notice that, hold on one second. I'm going to bring this down here for a second. This was all preliminary. Okay. Okay. So this is what I want to prove. I'm gonna rewrite this for a second. I'm going to say, okay, I'm going to say the following. I'm going to use the triangle inequality. I'm going to say the absolute value of A is equal to the absolute value of A minus B plus B. Okay. Exactly, they're the same thing. All I did was was kind of tricky. I added and subtracted a B, right?
Yes.
But now I can use the triangle inequality. Okay, I'm going to act like this is my A from before. And this is like my B.
Okay.
So I'm going to say this is less than or equal to the absolute value of the first quantity, right?
Yes.
Plus the absolute value of the second. Okay. And now what I'm going to do is I'm going to subtract the absolute value of B from both sides. Okay? So I'm going to do the following. So the absolute value of B minus the absolute value of A is less than or equal to the absolute value of A minus B. Okay, which one? On the first line or the second line?
The second.
Okay, so what I did here was I subtracted the absolute value of b from both sides, right? So notice that this is my inequality at this stage. At the end of the first step, I have this. I've shown that the absolute value of a is less than or equal to the absolute value of, hold on a second, a minus b plus the absolute value of b. Okay? So now all I'm going to do is I'm just going to subtract the absolute value of b from both sides. And I get this. Okay. Okay, now I'm going to do something kind of tricky. I'm going to start off the same thing, except now instead of a, I'm going to start with b. So I'm going to do the following. I'm going to start off now, and I'm going to say this. I'm going to say the absolute value of b is B. Yeah, B. Actually, this one, hold on a second. You know something? Actually, I take that back. Actually, well, let me think for 1 second. Hold on. We're actually proving B, but we could prove A at the same time. It's not that much more difficult, really. Okay, but let me go ahead and prove B, okay? Okay, so I'm going to play the same sort of game. I'm going to start off saying it's equal to B minus A plus A, right? And then I'm going to use the triangle inequality on this thing right here, right? So it's less than or equal to. Good. And now I'm going to subtract the absolute value of A from both sides, okay? So now I'm going to get this. Okay, less than or equal to B minus A. Okay? Now notice something. Notice that one of these quantities is negative. Well, let's put it like this. They could both be equal, could be 0, but let's suppose that absolute value of A is not equal to the absolute value of B, okay? So one of these is positive and one of these is negative, right? Okay, so you notice that this quantity, and let's just suppose let's just suppose that this is positive. We could make either one positive, but let's just suppose that this is positive. I'm going to make it greater than or equal to 0, right? So this means what? This means that B minus A is less than or equal to 0, right? Okay. So let's put this all together. So here's what we have. So we have that B minus A, absolute value of B minus the absolute value of A, is less than or equal to B minus A here. Okay? So I'm going to call this equation 1. I'll call this equation 2. And this is going to be 3, okay? Okay, so this is by 2. Right? And it's also less than or equal to, hold on a second. Hold on 1 second. Yeah, I'm sorry. That's right. Be careful here for a second. So this is greater than or equal to this, and let me back up a second. Let me think for a second what I want to do. Okay, let me start with this one. Okay, let me start. It's a little easier. Okay, so I'm going to say that is less than or equal to a minus b. Okay? Okay. And notice that if b minus a is less than or equal to 0, it's also greater than absolute value of b minus absolute value of a. Okay, so if we assume that this thing is positive, and this is greater than a positive number, then it's definitely greater than a negative, right? That's right. That's right. And so it'll also be less than this. Okay? Okay? Okay, so we know that this is greater than or equal to 0, right? And we know that this is also greater than or equal to b minus absolute value of b minus absolute value of a. Hold on a second. Absolute value of b minus absolute value of a. Because if we assume this is positive, this has to be negative, right? So this automatically follows. We get this for free. Now notice something. One of these guys, this is the key part. One of these guys is the absolute value. Okay, one of these guys is positive, right? Yes. And I've assumed that it's actually this guy here, right? Yes. So it's equal to its own absolute value, right? Right. So now we have what we want. We have our final result. We know that the absolute value of a minus the absolute value of b is less than or equal to the absolute value of a minus b. It's kind of tricky. These are little tricks you learn. You're not expected to know these. Nobody knows these at the beginning, okay? Well, okay, so you actually could. So let's go ahead and suppose, how would we prove the opposite side? Well, we have to start off supposing that b minus a, the absolute value of b minus a is greater than or equal to 0, right? So the other case we have to prove here, but it's really the same thing when you think about it. Here we just assume that the absolute value of b minus the absolute value of a is greater than 0. But notice the proof will be exactly the same way. You should actually, but it'll be the same sort of proof because here, this will be greater than or equal to 0. You just change the b to an a and change the a to a b, right? And you'll get the same result, okay? So we do these differently. So you notice how we combined all these laws, okay? This first one, actually, we didn't do too much here. We basically used the triangle inequality, okay? Just in a very, very tricky way. Yeah, like I say, it takes a little bit of time. It's a little bit time. You have to just practice the proofs, and that's the only way you can do it, really. Okay. All right, good. Let me think real quick. And actually, the first one is easy to prove. The first one's very easy to prove. This you can show directly with the triangle inequality. Okay? One line. Okay. So the absolute value of a minus b is equal to the absolute value of A plus negative B. Now I'm going to use a triangle inequality. Less than or equal to, what should I write here if I use a triangle inequality on this?
It should be A minus B.
Close. It's A plus the absolute value of minus B. Okay? So these two things are being added, right?
Yes.
Okay, now what's the absolute value of negative B? It's the same as the absolute value of B, right? Because the absolute value of a positive and negative are the same number, right? So this is just one nice line. See how easy? Piece of cake. Alrighty? Okay, good. Alright. Let's see. So that does 1.2.5. Okay. Let's see. 1.2.10. Sure, go ahead.
First time, most of my life, but they are very still because the Wi-Fi doesn't work.
Sure.
She is next to me. She is afraid.
No, that's okay. That's okay.
We had a time.
Here, hold on. Let me go back to my regular screen. Stop sharing. Okay. There we go. Okay, so you want to stop for right now? Sure. No. Mm-hmm. No, I understand. Where do you live? Oh, okay, yeah, that's where Abdul lived for a while. Yeah. I actually stayed. I don't know if he ever told you, but I actually stayed with him for a little while. Yeah, we were roommates for like a semester. Yeah, so. Yeah, I don't live in Ohio. I live in Indiana now. Not too far. I'm about an hour and a half away. So it's not too bad. Okay, you're not going to get to that stage till the summer, right? Okay, I'm going to actually be back in Dayton in the summer. Okay, because I actually work with people in Dayton, so I'm going to be there in the summer, so we can work one-on-one. I mean, I'll actually be in Dayton, so we can actually work together in the summer. Well, I can physically be there. Okay? Yeah. Good. I like Dayton actually. I kind of like it. Yeah. It's not too bad. Not real high crime for the most part. Low cost of living. Pretty good. So. Used to be where? I know because your area code is 412, and I grew up in Pittsburgh. I went to. Do you know Carnegie Mellon? That's where I went to school at. Yeah. Where did you... Oh, okay. Yeah. So they have... So that's... Is Point State Park... That's a community college, right? Is that community college? Or is that a regular college? I forget. Regular college. Okay, yeah. So Point State Park, that's downtown Pittsburgh. Is that right? Okay, cool. I love Pittsburgh. Did you like it? So do I. Are you serious? Wow. Yeah, I love everything about it myself. I wish I could go back. Yeah. So good food and You know, it's just, yeah, it's a lot of fun. So, cool. I would love that. Yeah, yeah. I can show you some things, and then you can show me what you know, what you know. Absolutely, you got it. All right. Okay, I'm gonna let you go. I'm gonna make a video now. It'll take a little while for the video, but I can send you the PDF of what we did, and then we can work together tomorrow. Okay. Tomorrow, I know in the evening I'm free. The evening's good. Like after 6 is good. Before then, I don't know. I know before 2 is bad. So if you want to, we could try like between 2 and 5, if that's good, or we can try after 6. Okay, I'll tell you what. Let me kind of see how things are going. But which is better for you? Is it better to work during the day?
Yes.
Okay.
Almost after 6. I mean,
Okay. Okay. Yeah. Probably around noon. I'll know for sure. Is that okay? I can tell you for sure around noon. Is that okay? Okay. Good. Good. All right. Sounds good. Okay. Get home to your wife and make sure she's okay. Alrighty. Okay. I'll see you soon. Take care. All right. Bye bye.